Today we are beginning our study of calculus. This is the first unit in calculus. This is the first unit you'll see whenever you start calculus. And we are going to take a look today at an intro to limits. We're going to talk about an intro to limits, and then we're going to talk about one-sided limits and finding a limit from looking at a graph. So first of all, the concept of a limit is very important in calculus, and calculus itself is very important. So I'll let you guys read that. I'm not going to read it to you, but if you want a nice intro, a nice visual intro, found one on YouTube at that site. Okay, that's the site for it. All right, so first of all, what is a limit? I like to think of a limit as the intended height of a function at a certain value of x. Know that the height is the y value. So when we find a limit, it's going to be the y value that is the intended height of the function at a certain value of x. It's the value that the function thinks that it's going to. Whether or not it gets there is irrelevant. We only care about the value that it's intending to be, that it's approaching. Okay? That is what a limit is. So let's begin by considering this function. This is a cubic function. I see the graph here. It does not have a denominator, so there's nothing funny going on. It's just a nice smooth curve. The height of the function, or its y value, changes as x goes from left to right. Of course, the y value changes as x goes from left to right. Let's look at what happens as x goes towards 1 from the right. Let's take a look at what happens when x goes towards 1 from the right. So here's 1, and we are approaching x from the right side. Okay? Know that we don't care what it is exactly at 1. We only care what is happening as we approach 1. And as we approach 1, the function is approaching -2. Yeah? What we're talking about there is called a one-sided limit. As x approaches 1 from the right or from the left, that is a one-sided limit. Okay? We have special notation for a one-sided limit. The notation is, if we're approaching from the left, we have a little negative sign on that x value. If we're approaching from the right, we have a little positive sign on the x value. We abbreviate limit with LIM, and you always, not just sometimes, you always write the function that you are taking the limit of right here. Never ever just write limit without writing the function or something beside it. It makes no sense to just say limit of nothing. Okay? So, as we approach, let's go over here since we already drew that. Let's go over here. So we're approaching x x is approaching 1 from the right. So x is approaching 1 from the right. What is y approaching? Well, y is approaching -2. So this one-sided limit would be -2. Okay? If we approach -1 from the left, then we're coming at x is approaching -1 from this direction. And what is happening to the curve? Well, the curve is still approaching -2. So that limit is -2. Okay? If the limit from the left-hand side is equal to the limit from the right-hand side, we say that the entire limit as x approaches 1 is that value, -2 in this case. So, you might be wondering why we do this. Okay? I would be if I used that as an example. Limits get way more interesting. So this was just a very brief intro. Let's take a look at something else. let's take a look now at a function g, and this time g does have a denominator. The denominator is x minus 2. So it is a cubic, but it has a denominator, x minus 2. And we could factor that numerator, and when you factor that numerator, we see that the same factor on top is on the bottom. That means we have a hole in the function, and sure enough, there is a hole in the graph of that function. So the hole is at x is equal to 2, and if we canceled that out and plugged in 2 to what remained, we'd have 2 squared. That would be the point 2, 4. So there is a hole at 2, 4. Okay? All right. So that is why the graph has a hole at 2, 4. Now, let's find the limit as x approaches 2 from the left. So as we approach 2 from the left, when x is approaching 2 from the left, the function is approaching 4, right? Correct? So that left-hand limit is 4. From the right-hand side, if x is approaching 2 from the right-hand side, then the function value is still approaching 4. If they are the same values, then the limit as x approaches 2 is that same number, 4. So know this, we do not care, we don't care what it is right when x is 2. We don't care. It could exist there or not. We could make this a piecewise function and put this point elsewhere, right there. It doesn't matter. The limit is still 4. Let's consider this piecewise function. Speaking of piecewise functions. So we have a parabola when x is less than 2, and we have a line with a negative slope when x is greater than or equal to 2. Let's find the limit as x approaches 2 from the left of this function. So we're approaching 2 from the left. The function is approaching 4. The y value is approaching 4. When I say the function, I mean the y value, because f of x is equal to y here. Now let's approach x from the right-hand side. If we approach 2 from the right-hand side, the function is approaching 5. So the limit as x approaches 2 would not exist. It does not exist, because the limit from the left is not equal to the limit from the right. So it does not exist. We have this response a bit frequently, so we abbreviate this DNE. Does not exist. Okay? All right. So here is a nice the graph of a piecewise function g. And let's use this graph to answer all of these questions over here. So first let's approach positive 1 from the left. So positive 1 from the left. What is f doing as x approaches positive 1 from the left? Well, positive 1 from the left would be up here. The y value is approaching 7. So this limit is 7. Now, right when it gets to 7, the function value is way down there at 2. But we only care what it's approaching, and it's approaching 7. Let's go from 1 from the right-hand side. From the right-hand side, the function value is still approaching 7. It is approaching 7. It thinks it's going to get to 7. It's intending to get to 7. The intended height is 7. Okay? So what is the limit as x approaches 1? Are they the same thing? Yes. then that limit is that same value. Okay? What is this asking? This is asking for the function value at 1. What actually is g of 1? G of 1 is 2. That is just 2. Okay? Let's go now to x is going to 6 from the left. 6 from the left. So 6 from the left, there's x approaching 6 from the left. Where's the function? The function is approaching 2. The function thinks it's going to get to 2. It's intending to go to 2 from the left. What about from the right? From the right, the function is up here, and it thinks it's going to get to 3. Are these the same? Does this exist? No. As x goes to 6, this limit is non-existent. It does not exist. Now, what actually is g of 6? Well, g of 6 is 3. This is a lot about reading the graph. Let's approach -2 from the left. As we approach -2 from the left, as x approaches -2 from the left, the function value is approaching 0. It thinks it's going to go to 0. Whether or not it gets there, we don't care when we're talking about a limit. Let's approach x now from the right. I'm sorry, let's approach -2 from the right. From the right, the function is up here, and it thinks it's going to get to 4. It thinks it's going to be 4. So this limit, as x approaches -2, does not exist. It is non-existent. But what actually is g of 2? G of 2 actually is 0. All right. As x approaches -5 from the positive side, well, let's go find -5. -5 from the positive side would be right here. The function value, or the function is up here. It thinks it's going to go to 2. So that as x approaches -5 from the right, g of x is 2. Let's approach 8 from the left. 8 from the left will be right there. 8 from the left, the function value is approaching 3. So that limit would be 3. So the piecewise functions make for some very interesting graphs. Okay. Let's take a look at this one. Let's take a look at this function. F of x is x minus 1 over 2x minus 4. If I factor this denominator, I get x minus 1 over 2 times x minus 2. Is there a hole? No, there is no hole. There is, however, a vertical asymptote. At x is equal to 2. And we see that vertical asymptote here. So if there is no hole, the factor that remains will give you a vertical asymptote. Sometimes more than one vertical asymptote is in a function. All right, so we want to know, we're going to be talking about limits of infinity and limits at infinity. First, we're looking at limits at infinity. So we want to know what is happening to the function as x increases without bound. As x increases without bound. So x is going to infinity. Here x is going, the graph only shows x going to 10. Let's ask ourselves what happens as x goes to infinity. as x goes to infinity, what is y approaching here? So what is that y value? What's the y value there? Okay. And at this point, I'd probably ask my students for some guesses. What do they think that that y value is? It's looking like it's about a half, right? So that makes me go and examine the function. And does it make sense that that horizontal asymptote would be at 1/2? It sure does, because as x approaches infinity, this -1 will be irrelevant, this -4 will be irrelevant, and those x's reduce to 1/2. So that limit is 1/2. This is called a limit at infinity. You don't have to know that though, but x is going to infinity. What is the y value approaching as x goes to infinity? So that's a horizontal asymptote. So if a limit goes to infinity, if a limit as x goes to infinity is a real number, not infinity, then you have a horizontal asymptote at that value of y. Also, if a limit as x goes to negative infinity is a real number, you have a horizontal asymptote at that value of y. So you can have two different horizontal asymptotes. Here it's the same horizontal asymptote, but you could have two horizontal asymptotes. Okay, one as x goes to positive infinity, one as x goes to negative infinity. All right, question. Can a function ever cross a horizontal asymptote? Okay. And the answer is yes, it can. A horizontal asymptote only tells you what is happening as x approaches positive infinity or negative infinity. It tells you nothing about what's happening to the function in between there. So you might want to write that down for your notes. A horizontal asymptote only tells you what is happening as x approaches infinity or negative infinity. It tells you nothing about in between there. It tells you nothing about finite values of x, the function value for finite values of x. Okay? So, if the limit as x approaches infinity of f of x is a real finite number, then f has a horizontal asymptote there. Also, if x approaches negative infinity of f of x, if that is equal to a real finite number, then f has a horizontal asymptote at that value. All right. It's not the same graph. It's a different graph now. Okay, let's consider this one. So we have this. There's no hole. There is a vertical asymptote. At x is equal to 4. Vertical asymptote at x equals to 4. Because that makes x is equal to 4 makes that function undefined. So we do have a vertical asymptote at x is equal to 4, and we can see that here. Okay, let's find the limit as x approaches 4 from the left. So x is approaching 4 from the left. 4 from the left. What is y doing? What is happening to y? As x gets closer and closer and closer to 4 from the left, what is y doing? Well, y is going to infinity. Negative infinity. Y is going to negative infinity. right? What happens as x approaches 4 from the right? Well, from the right, the function value is going to positive infinity. What is the limit as x approaches 4? Does not exist. And I will say that it does not exist not because these are different infinities, but because they are infinity of any kind. Even if they were both infinity, this limit would not exist. All right? Infinity is a special kind. So plus or minus infinity is a special kind of does not exist. It's a special kind of DNE, does not exist. Okay, very similar to a square is a special kind of quadrilateral, right? Well, infinity is a specific kind of does not exist. There are other kinds of does not exist, but infinity is one of them. Negative infinity is one of them also. Okay? Can a function ever cross a vertical asymptote? Can a function ever cross a vertical asymptote? So I would let my kids in class answer that, but most of them would say, I don't think so. A single equation for a function would not cross a vertical asymptote, but a piecewise function can. Okay? And we do deal with a good number of piecewise functions in calculus. You'll get more familiar with that. So, if a limit as x approaches a from the left of a function is either positive or negative infinity, okay, where a is a finite number, then f has a vertical asymptote at that value of a. Okay? Same thing if it approaches a from the right, a vertical asymptote. And infinity is a special kind of DNE. All right, how are we doing on time? Not too bad. Good. I was a little curious. When I saw that I was making 4 pages of notes here, I was a little curious how long it would take. All righty. So, some things to keep in mind when you're looking at a graph to evaluate a limit. Every one-sided limit exists, which means it's a number, unless the limit is infinity or negative infinity. For a regular limit, not one-sided, if there is a hole, the limit does exist and is the y value of that hole. Also for a regular limit, not one-sided, if there is a break in the graph, not a hole, but a complete break, the limit does not exist because the limit from the left would not equal the limit from the right. The limit as x approaches infinity or negative infinity gives you a horizontal asymptote if there is one. If you get a limit of infinity, you have a vertical asymptote. If x is a real number, if the value that you are using for x is a real finite number. Okay, limits of infinity or negative infinity are a special kind of DNE. Okay. All right, let's sum it all up here with this piecewise function. Okay, we have this piecewise function is graphed for x is greater than -8. Evaluate each limit if possible. If not, we're going to write DNE. So this would be one where the kids in class would do these problems. I'd walk around, see how they're doing, see if they have any questions. So let's approach -6. So if you want to try it on your own, and then come back and check your answers. I'm going to approach -6 from the left. -6 from the left the y value is approaching 2. -6 from the right, the function is approaching 2. Since these are the same, the limit as x approaches 6 is that value. What is the function value at -6? It is also 2. So those were all 2. Let's approach -4 from the left. -4 from the left, the function is approaching 4. So this limit is 4. Let's approach -4 from the right. -4 from the right, the function is approaching 3. So the entire limit as x approaches -4 does not exist because the limit from the left was not equal to the limit from the right. What is the actual function value at -4? 4. That's where that dot is. So that's 4. Okay, let's approach 3 from the left. 3 from the left. Positive 3 from the left. So 3 from the left, we're going to be down here, and the function is approaching -3. So that limit is -3. 3 from the right. Well, 3 from the right, the function value is approaching 2. So that limit will be 2. Since those are not the same, this limit does not exist. The actual function value, f at 3, is 2. Alright, some random ones. What's happening as x approaches 0? Now there's not a one side on there, so we have to consider both sides. As x approaches 0, from the left and the right, are those the same thing? They are the same thing. It's going to 3, so this limit is 3. What is f of -2? What is f of -2? f of -2 is 1. What's the limit as x approaches -8 from the right? -8 from the right. Where's our function? Our function is way up here, and what's it approaching? It is approaching infinity. That means we have a vertical asymptote there. It's infinity, which is a special case of DNE. This is how I would like you to write it. If you do get infinity, I'd like you to write infinity, and then parentheses DNE, because it is a special type of DNE. If back in geometry you had a square and you said that it was a square, you wouldn't necessarily write underneath it, that's also a quadrilateral, right? But I do want you to say that it is a non-existent answer. Okay, what happens as x approaches infinity? What is the function value as f approaches infinity? So as x approaches infinity, what is y approaching? What is y getting closer and closer and closer to? Y is getting closer and closer to 4. So this limit is 4. And that is how to use a graph to find a limit, and it's our introduction to one-sided limits.